applications, exponential function applications. That's where we're at now. Lots of words, but we're going to sort through them. We're going to break this down. It says the balance of an account in which interest is compounded periodically is given by A equals P times 1 plus R over N to the NT, where T is my time in years, R is the annual interest rate as a decimal, N is the number of times per year the interest is compounded, P is the principal, that initial amount of money, and A of T is the amount in the account after T years. Okay, so let's talk about a couple of things related to this compound interest formula. Your rate is going to have to be written as a decimal. So if they give it to you as a percentage, we've got to convert that over to a decimal. And N is the number of times per year the interest is compounded. So let's kind of make a little list for ourselves real quick. If something is annual, it's going to be compounded 1 time a year. If it's semi-annual, it will be compounded twice a year. If it's quarterly, this one's going to be 4 times a year. Monthly would be 12 times a year. And I'm not sure we come across any, but if it's daily, it would be 365 days a year. So those are good terms to reference numbers that you want to make sure you know. In this particular problem, it says, suppose $1,000 is invested at 8% interest, compounded monthly for 40 years. How much will be in the account? So, right here I get 1,000 is that initial amount of money I invested, so P is going to equal 1,000. My interest rate's 8%, but remember I have to write it as a decimal. So my R value is going to be 0.08. And it's compounded monthly. Monthly means that it's going to happen 12 times a year, so N equals 12. And this is going to happen for 40 years, so T equals 40. All right, how much will be in the account? We essentially, at this point, got to plug and chug. We're going to have 1,000. Use those parentheses. 1 plus 0.08 over 12, all to the 12 times 40. Be careful entering this in your calculator. Make sure you're using parentheses where appropriate. Once you enter this in, you will need your calculator to do this calculation. You should get $24,273.39. If you're somebody that did not come up with that same number, double check it, try it again in your calculator. But again, if you still have trouble, let me know. All right, it's the moment we've all been waiting for. We are introducing Euler's number. Ta-da! Euler's number. Euler's number is E. Okay, now E is very similar to pi in that it's a number. It's not a letter in the sense of mathematics. It has an approximate value, kind of how we know that pi is about 3.14. We know that E is approximately 2.7182812828, so on and so on and so on. Keeps going, okay? If you're looking for Euler's number E on your calculator, E is above the division, okay? E to the X is above the ln button, okay? Generally speaking, I definitely use the one that's above the ln button. more often. Keep in mind that to access something like that, you are going to have to do second ln or second division in order to get that number. So it's all about that second button. Now, just to get some practice with that calculator, let's do some calculations with E, okay? Try pausing this video for a minute and try putting in the following into your calculator and see if they match up with mine. But again, this is really just a calculator exercise in terms of knowing how to enter it in. All right, so E cubed, we should get approximately 2.01. E to the 0.23, we should get approximately 1.3. So just for reference in this problem, I'm just rounding to 1 decimal place. E to the negative 2, you should get just about 0.1. Now, e to the 0, to be honest, we really don't need to put into our calculator because we know anything to the 0 is 1. And e to the 1 is approximately 2.7. If you're having any issues with that calculation in your calculator, please reach out to me. Let me know. I am here to help. Okay. The value 2.71828 ... is called E. Okay. I mentioned this already, but it shows up very often when doing mathematical calculations. It's really very similar to pi in many ways. It is irrational. It can't be expressed as a fraction. It's not a square root of any number. It goes on and on and on and on and on. Okay. Now, in addition to our application problem where we had interest that was compounded monthly, quarterly, annually, semi-annually, we have what's called continuous compounding. Now, the reason we had to learn about E, or Euler's number, real quick is because the formula for continuous compounding uses it. Anybody ever use Pert shampoo? My dad uses it. That's how I always remember this formula. So the formula for continuous compounding is A equals PE to the RT. P is still that initial amount. R is still that interest rate as a decimal. And R is still that time in years. Okay, so we're going to follow this formula. It says you deposit $3,000 into an account. How much money will you have at 3% continuous compounding for 10 years? So my initial amount P is $3,000. We have a rate of 3%, so my R is 0.03, and my T value is 10. We are going to find out that we have 3,000 times E to the 0.03 times 10, which gives us a total of $4,049, and we'll round to 2 decimal places since we're talking money, 58 cents. Now again, this is something you need to just simply enter into your calculator. I typed in 3,000, then I did second ln, which gave me that e to the x. So the e showed up, and then I typed in that exponent of 0.03 times 10 and hit my equal sign. Okay. All right, this next problem is a problem that comes up in your homework. It's a matching problem. And I like to go over in class typically because I tend to get some questions on it, okay? While you can do this one by entering it into your calculator, it can get a little confusing about which one's which, especially if your calculator screen is just black and white. But we can pick out a couple things on these based on the properties pretty easily, okay? Only one of these graphs has a y-intercept of 2, 0. And only one of these graphs, D, is going to actually give me that y-intercept of 2, 0. If I were to plug in 0 here, I'm going to have 1.28 to the 0, which is 1, times 2, which gives me 2. And let me actually fix this. It looks like the superscript didn't transfer over. All these x's should be in the exponent position. So D is the easy one to pick out because it has a different y-intercept right off the bat. Now, something else that we can take note of is the value of the base to determine if it's increasing or decreasing, okay? Notice that A and C, that A value is less than 1, so we know that A and C are going to be decreasing. In B and D, or B and E, those values are over 1, so we know those two are going to be increasing. So in terms of that, A and C have to be the blue and the black line, and B and E have to be that red and orange line, okay? Now, B is going to increase faster than E, and that's because its A value is higher, okay? B will increase faster than E. So if that's the case, when I look at these graphs, I know that B is that orange line and red is the E. Now, if I look at the blue and black line, my two decreasing, I know that A is going to decrease faster than C. So I know that that blue line is A and that black line is C. So again, we can use our graphing calculator here to help us match them up. But if we use some of that other knowledge that we've gained so far about the intercepts and increasing and decreasing, we also can pair them up that way as well. All right, this time we have a certain radioactive material that decays in such a way that the mass remaining after T years, there's a T missing there, is given by the function m of t equals 140 e to the negative 0.05 t, where m of t is measured in grams. So we are focusing on this function m of t. First thing we want to find is the mass at time t equals 0. So that means we're going to plug in 0 for t. So we're going to have m of 0 equals 140 e to the negative 0.05 times 0. Now, following our order of operations, we need to multiply negative 0.05 times 0 in our exponent first, which gives us 0. So we have 140 e to the 0. Now we know e to the 0 is 1, so we're going to have 140 times 1, which is simply 140. And that should be in grams. Now, you could throw that in your calculator, but with that exponent of 0, we really could do it mentally as well. Okay, part B wants to know how much of the mass remains after 40 years. Okay, and you will need to answer this one in your calculator, and we're going to put all the digits that our calculator displays. Okay, Now, this means that for my t value, I'm going to plug in 40. So I'm going to have 140 e to the negative 0.05 times 40. When you plug this into your calculator, you should get 18.9469365, and we are still talking grams. Okay. Now think about this too. If you know that at time 0 you had 140 grams and this material is decaying, your answer for after 40 years should be less, which it is. So just make sure you're checking in with the reality of what's happening in your answer in relationship to the application problem itself. Okay, this one says a population numbers 16,000 organisms initially and decreases by 5.6% each year. Suppose P represents population and the T, the number of years of growth. An exponential model for the population can be written in the form where P equals A times B to the T. Only thing they want us to determine in this problem is what my equation would look like. So where it says where P equals, they want us to fill in A and B. Okay. Now, my initial value is this 16,000 organisms. That's that A value. Okay. My B value decreases by 5.6%. If something decreases by 5.6%, that means it retains 94.4%. The way you can get that is do 100 minus 5.6, and you're going to get 94.4. 94.4% is how much it retains each year. But remember, we can't write our percentage, our rate as a percentage. It has to be a decimal. So this B value is going to be 0.944. We had to move that decimal place 2 to the left. So my P value would be 16,000 times 0.944 T. So we're simply writing a model in this scenario. We're not getting out an actual answer for the number of years on this one. Notice too that this particular problem said decreases. In your homework, depending on which version you get, you might get an increase or decreasing. So what if it was increasing? Then instead of subtracting it from 100, we would add it to 100. And we would get that it would be 105.6%, which when we write it as a decimal would be 1.056. So be aware of the difference the word increasing and decreasing makes in this type of problem. All right, our next problem is a depreciation problem, which again means that it's decreasing. We have a vehicle that was purchased for $32,500 that depreciates at a constant rate of 9%. Determine the approximate value of the vehicle 11 years after purchase. Round to the nearest whole number. Now, this particular problem is going to follow that same model of P equals A times B to the T. Now, that initial value of my vehicle was $32,500. My rate, that B value is 9%. But remember, we have to write it as a decimal, and it's also depreciating. So we need to do 100 minus 9, which is 81%, which is going to be 0.81 for my B value. I can't subtract apparently. How about 91%? Sorry about that. It's crazy time. All right, so my B value is 0.91, 91 hundredths. So I'm going to have the following: 32,500 times 0.91. Now my T value in this problem is 11. And this is something I am going to have to enter into my calculator, and it wants me to round to the nearest whole number. When I do that, I'm going to get $11,517. And that's it for our application problems. Let me know if you have any questions.